Hello students, today we are going to the next section, functions. The topic functions is the most essential part of modern mathematics. If you are dealing with either physics, chemistry or even social sciences, you have to go through a lot of functions. Let us take a simple example from physics. Consider this car moving with a uniform acceleration for some time. Here we can associate two quantities with the movement of this car. One is time and the other is position. Let after 1 hour, the car has reached 10 kilometers away from the starting point. After 2 hours, let the car has traveled 40 kilometers away from the starting point. After 2 hours, let the car has traveled 40 kilometers away from the starting point. Thus, we are connecting two quantities, time with position. Note that at each time the car takes a unique position, or we can say position is a function of time. At each time the car takes a unique position, or we can say the position is a function of time. We write position P equals a function of time, f of t. P equal to function of time. If we denote this process in a graph, in a position time graph, you have studied position time graphs in first year physics. Time in the x-axis and position in the y-axis. Time in the x-axis and position in the y-axis. The graph drawn will be a parabola like this. This is the graph of the function p equal to f of t. Let us take another example from economics. It is the price movement of a stock in a particular day. Boluram had bought 1000 shares of ITC at 200 rupees. By the evening, the price moved to 210 rupees. He got 10,000 rupees profit in a single day. See, the price movement is a function of time, since at each time the share takes particular values, random values. Now let us go to the formal definition of a function. A function, a relation defined from set A to set B, is said to be a function if every element in A has one and only one image in B. You recall what you studied in the last year? If every element in A relation from set A to set B, is said to be a function if every element in A has one and only one image in B. Is this relation a function? The first figure does not represent a function. Why? Here, the element 4 has no image in B. The second figure also does not represent a function. Why? There are two reasons. First of all, 3 has no image in B, and Moreover, the element 2 in A has 2 images in B. That is not allowed for a function because uh, just recall the position time graph we drawn for the movement of that car. A car cannot take two positions at the same time. At the same time, the car cannot take two positions. Therefore, this is a similar case and the second relation is not a function. And is it a function? It is a function because each element has one and only one image in B. Each element in A has one and only one image in B. But you might have a doubt. The elements 2 and 4 have the same elements, same images in B. Then can it become a function? Of course it can become a function because let us consider the syntax graph we discussed earlier. The syntax graph we discussed earlier. At two times, say at 9:30 am and at 2:30 pm, the share can take the same values. Do not say the share can take the same values 205 rupees. Therefore, it is similar. This case is similar to that problem. At 2 and at 4, it can take the same values b. Therefore, it is also a function. Similarly, it is also a function. Here, the elements 1, 2, 3 and 4 in A has the same image, A, small letter a, in B. Thus, the definition of a function is that a relation from A to B is said to be a function if every element in the set A has one and only one image in B. One and only one image in B. A magician gave me this machine. If we put something in this machine, the machine will multiply it in such a way that first the machine doubles it and then 3 is added to it. First the machine doubles it and then 3 is added to it. If I put a ball into this machine, if I put a ball into this machine, the ball will give me, the machine will give me how many balls in return? First it doubles it, that is 1 into 2, 2. Then 3 is added to it, that is 2 plus 3, 5. I will get 5 balls. This machine gives me 5 balls in return. This is a magic machine. See, I can put anything I like into this machine. If I put an elephant into this machine, if I put an elephant into this machine, see, I am putting an elephant into this machine. The machine will give me back, I am putting an elephant into this machine. The machine will give me back 5 similar elephants. And if I put two pencils into this machine, the machine will, if I put two pencils into this machine, the machine will give me back how many pencils? First, it is doubled. 2 into 2, 4 plus 3. That is, the machine will give me back 7 pencils. Thus, if I put 1 into this machine, the machine will multiply it into 1 into 2 doubles 8 plus 3 is added. That equal to 5. And if I put 2 into this machine, I will get 2 into 2 plus 3 equal to 7. If I put 3 into this machine, I will get 2 into 3 plus 3 equal to 9. And what if I put x into this machine? I will get 2 into x plus 3 equal to 2x plus 3. And it is the function of the machine. See, x becomes 2x plus 3. The function of the machine is that x is turned into 2x plus 3. That is f of x. In mathematical language, f of x equal to 2x plus 3. That is, x has become 2x plus 3. Plus, the function of the machine is that if we put x into it, that is, if x is the input, let we get y as the output. Then y equal to 2x plus 3. Y equal to 2x plus 3. Or the function of the machine in function language is f of x equal to 2x plus 3. When f of x equal to 2x plus 3, you know that f of 1 equal to 2 into 1 plus 3 equal to 5. When x equal to 2, we have f of 2 equal to 2 into 2 plus 3 equal to 7. And when x equal to 3, f of 3 equal to 2 into 3, 2 into x equal to 3, 2 into 3 plus 3 equal to 9. Thus, we have summarized the function of the machine in mathematical language as f of x equal to 2x plus 3. The main use of mathematics is that anything can be explained shortly in a language called mathematical language. Now let us represent the data in an arrow diagram. The input, and it is a function, let it be a function defined from the set of all natural numbers to the set of all natural numbers. The domain of the function is 1, 2, 3, 4, etc. And the range and the codomain of the function is also 1, 2, set of natural numbers 1, 2, 3, 4, 5, 6, 7, etc. Let us use an arrow diagram. Here 1 is related to 5. When 1 is the input, 5 is the output. Therefore, 1 is related to 5. 1 is related to 5. And 2 is related to 7. When 2 is the input, 7 is the output. 2 is related to 7. And 3 is related to 9. Let us write 8 and 9 also. 3 is related to 9. When 3 is the input, 9 is the output. 3 is related to 9. And similarly 4 is related to. Thus, it is clearly a function because every element in the first set has its own image in the second set. When the input is 1, the output is 5. Let us find a reverse relation. That is, when the input is 1, the output is 5. If the output is 5, what is the input? When the output is 5, then the input is 1. When the input is 2, the output is 7. And in the reverse order, when the output is 7, the input is 2. And similarly, when the input is 3, the output is 9. And when the output is 9, then the input is 3. We have f of x equal to 2x plus 3 or y equal to 2x plus 3. Y equal to 2x plus 3. If we put any value for x, we will get the value of the output y. And we are making a reverse relation. Can we find x from this? Yes, we have 2x equal to y minus 3. 2x equal to y minus 3. Or x equal to y minus 3 divided by 2. Y minus 3 divided by 2. That is, when the output is 9, we put y equal to 9. If y equal to 9, then the input is given by x equal to 9 minus 3 divided by 2. That equal to 6 by 2 equal to 3. That is, when the output is 9, we found a formula for getting the input. When the output is 9, the input is 9 minus 3 divided by 2 equal to 3. When the output is 9, the input is 3. Thus, we have found the reverse relation. The original relation is that y equal to 2x plus 3 and the reverse relation is that x equal to y minus 3 by 2. The original relation gives the value of the output when input is known and the reverse relation gives the value of the input when the output is known. Now, the next question is that what will be the input if the output is 3? What will be the input if the output is 3? For this, we have x equal to y minus 3, x equal to y minus 3 divided by 2. When the output is 3, we have to substitute 3 for y. When the output is 3, 3 minus 3 divided by 2. That is x equal to 0. But x equal to 0 is not a natural number and we cannot find the input when the output is 3. Thus, the reverse relation exists if and only if some conditions are satisfied. See, the reverse relation exists if and only if the reverse relation exists if and only if some conditions are satisfied. We are also sure that when y equal to 8, we cannot find the input. When y equal to 8, what happens? X equal to, when y equal to 8, x equal to 8 minus 3 divided by 2, that equal to 5 by 2 equal to 2.5. When y equal to 8, x equal to 2.5. When the value of y is 8. When the value of y is 8, the value of x is 2.5. And 2.5 is also not a natural number. Thus, the reverse relation exists if and only if some conditions are satisfied. We are going to check, or we are going to find the conditions for the inverse relation exists. Thus, we are moving to the main part of our chapter or topic, the 1-1 function and the onto function. The 1-1 function and the onto function. The first function f1, it is a function, and f1 is a 1-1 function because each one is related to only one. That is, the second element in the set has only one pre-image in the first set. See, while f2 is not 1-1, 1-2-1, as the name indicates, 1-2-1, 1 related to 1. But f2 is not a 1-1 function because here the element b in the second set has two pre-images in the first set. Element b in the second set has two pre-images 2 and 3 in the second set. Therefore, f2 is not 1-1. I think you got the point. f1 is 1-1 while f2 is not 1-1. f3 is also not 1-1. Why? f3 is not 1-1 because the element b here has two pre-images 2 and 4 in the first set. Therefore, f3 is not 1-1. What about the function, last function f? It is clearly 1-1. 1 is related only to 1. Therefore, the function is clearly 1-1. If the function is not 1-1, it is called a many-one function. Here, f2 is a many-one function. B has two pre-images. And f3 is a many-one function. While f1 and f are 1-1 functions. 1-1 function is also called an injective function. The next one is an onto function or surjective function. Onto function. It is not an onto function because the element d in the second set has no pre-image in the first set. Therefore, the function f1 is not an onto function. Therefore, the function is an onto function if every element in the second set has a pre-image in the first set. It is not an onto function. It is also not an onto function. Why? The element C in the second set has no pre-image in the first set. Therefore, f2 is also not an onto function. Is f3 an onto function? Yes, f3 is an onto function because every element in the second set has a pre-image in the first set. Is the last function f an onto function? Yes, it is also an onto function because every element in the second set has a pre-image in the first set. If the function is not onto, it is called an into function. It is called an into function. Here f1 is not an onto function. It is an into function. f2 is also not an onto function. It is an into function. It is an onto function, and the last function is also an onto function. And look at the last function f, denoted by f. it is clearly 1, 1 and onto 1, 1 because every element is related to one element. Therefore, it is a 1, 1 function, and it is an onto function because no element in the second set has there exists no element in the second set such that it has not a preimage. Therefore, it is an onto function. The function is 1, 1, both 1, 1 and onto. Such functions are called bijective functions. A function is said to be a bijective function. The third one, 3. Bijective function. Bijective function. A function is said to be a bijective function if it is both 1, 1, 1, 1 and onto. If the function is both 1, 1 and onto, it is called a bijective function. The importance of a bijective function is that we can find a reverse relationship. See, it is a bijective function. The fourth function is a bijective function since it is both 1, 1 and onto. The importance of a bijective function is that if there exists a function from A to B, we can find a reverse function from B to A. We can find a reverse function from B to A. Thus, we have to study about the 3 types of functions. First one is 1, 1 function or injective function. Second one is onto function or surjective function. And the third one is bijective function, which is both 1, 1 and onto. And the importance of a bijective function is that if there is a function exists from A to B, then we can find a reverse function from B to A. Let us go to a problem. The question is that show that the function f defined from n to n, set of natural numbers to set of natural numbers, given by f of x equal to 2x is not an onto function. The relation is that f of x equal to 2x. Clearly 1 is related to 2. 1 is related to 2. 2 is related to 4. The element 2 is related to 4. The element 3 is related to 6. Element 3 is related to 6. The arrow diagram shows that the function is not onto because the elements in the second set 1, 3, the odd numbers, odd natural numbers 1, 3, 5, 7, etc. have no pre-images in the first set. Therefore, the function is not an onto function. That is, the range not equal to, the range is 2, 4, 6, etc. Range of the function is 2, 4, 6, etc. is not equal to the second set itself. Therefore, the function is not an onto function. Once more, the elements 1, 3, 5, 7, etc. in the second set have no pre-images in the first set. Therefore, the function is not onto. But clearly the function is 1, 1. See, 1 is mapped to 1. 1 is, the image of 1 is 2, the image of 2 is 4, image of 3 is 6. The elements in the second set have distinct pre-images in the first set. Therefore, the function is clearly 1, 1, but it is not onto. Now to the next problem. Show that the function f defined from R to R, set of real numbers to set of real numbers, defined as f of x equal to x squared is neither 1, 1 nor onto. It is not 1, 1 and not onto. F of x equal to x squared. F of x equal to x squared. What is f of 1? the image of 1, f of 1 is 1 square, that equal to 1. And what is f of minus 1? F of minus 1 is minus 1 square equal to 1. See, the function is defined from real numbers to real numbers. Therefore, the numbers 1 and minus 1 are related to the same number 1. The image of 1 is 1 and the image of minus 1 is also 1. Therefore, the function is not 1, 1. And we have to prove that the function is not onto. The function becomes the function defined from real numbers to real numbers. Real numbers to real numbers. The function becomes onto. The function f defined from R2 or real numbers to real numbers. It becomes onto if some elements in the second set 0, positive numbers such as 1, 2, 3, 1.5, 1.7 and negative numbers minus 1, minus 2, etc. And here also 1, 2, 2.5, 1.3, minus 1, minus 2. All are real numbers. And we know that, we have proved that the image of 1 is 1 and the image of minus 1 is 1. Therefore, the function is not onto. Therefore, the function is not 1, 1. To prove that the function is not onto, we know that the function is defined as f of x equal to x square. That is, real numbers are squared. Here, if we take the square of a number, we will not get negative numbers as answer. If we take the square of any number, we will get only 0 or positive numbers. We will not get negative numbers. That means the negative numbers like minus 1, minus 2, minus 3.5, etc. have no pre-images in the first set. Therefore, clearly the function is not onto. Thus, the function is neither 1, 1 nor onto. Now let us give a graphical interpretation of the problem. The function is f of x equal to x square or y equal to x square. We can say y equal to x square. And you have drawn the graph of this function. The graph of this function y equal to x square last year. It is a parabola. The graph of the function is a parabola. It was drawn by giving some values for x and y. When x is 0, y equal to 0 square 0. When x is 1, y equal to 1 square 1. And 2, x equal to 2 square 4. And if it is minus 1, minus 1 square 1, minus 2, the y value is minus 2 square 4, etc. And we have drawn the graph of the function as a parabola. Here we have the image of, when x equal to 1, the value of y is 1 square 1. And also when x equal to minus 1, when x equal to minus 1, the value of y minus 1 square, that is 1. Therefore, the function is not clearly 1, 1. The 1 and the numbers 1 and minus 1 have the same y value 1. The function is not 1, 1. There is a graphical test to check whether the given function is 1, 1 or not. It is that if we draw a line parallel to the x-axis, if we draw a line parallel to the x-axis and if it cuts the graph at more than 1 points, and if the line cuts the graph at more than 1 points, the function is not 1, 1. For example, let this point is 2. The y value of 2 is 2 square 4, and let this point is minus 2. The y value of minus 2 is also minus 2 square 4. Therefore, 2 and minus 2 have the same y value. Thus, parallel line test helps us to check whether the function is 1, 1 or not. I think you have got the point. To check whether a function is 1, 1, we have to draw the graph of the function. It is a parabola here. If we draw a line anywhere, if we draw a line parallel to the x-axis, and if it cuts at more than 1 point, it is not a 1, 1 function. Also note that last year we have drawn the graph of the function f of x equal to x cube or y equal to x cube. If you remember, the graph of the function takes this shape. It is the graph of the function y equal to x cube. We can see that from the graph itself, we can see that it is clearly 1, 1, because if we draw a line parallel to the x-axis anywhere, it cuts the graph only at 1 point, not at 2 or more points as shown in the graph of the function y equal to x square. Therefore, if anywhere we draw parallel lines, it cuts at only 1 point. Therefore, the function is 1, 1. Let us come to the next problem. The problem is that show that the function f defined from R to R, defined as f of x equal to 2x, is both 1, 1 and onto. We have done the same problem for f from n to n. Now the problem has been changed to f of x equal to 2x defined from real numbers to real numbers. In the previous problems, we were proving that the function is either not 1, 1 or not onto. To disproving a problem, it was enough to take a counter example. But now we have to prove this problem, prove this property. So we have to do it theoretically. The theoretical way of proving that a function is 1, 1 is that if f of x1 equal to f of x2, if f of x1 equal to f of x2, it implies x1 equal to x2. Whenever f of x1 becomes equal to f of x2, then x1 becomes x2 if the function is a 1, 1 function. Let us go to its meaning. Let there are two elements x1 and x2 in the first set. Let their images are f of x1 and f of x2. F of x1 and f of x2. The image of x1 is f of x1 and the image of x2 is f of x2. Unfortunately, now the function is a 1, 1 function. With the two elements x1 and x2, the function seems to be a 1, 1 function. Unfortunately, let f of x1 becomes same as f of x2. Let f of x1 becomes equal to f of x2. F of x1 equal to f of x2. Now the arrow mark, the image of x2 is also the same point. Clearly, the function seems to be not 1, 1. But if it is 1, 1, the only way it to be 1, 1 is that x1 becoming equal to x2. If x1 and x2 is also the same, if x1 equal to x2, if x1 becomes equal to x2, f of x2, if f of x1 equal to f of x2 and the function has to become a 1, 1 function, then x1 should be equal to x2. It is the theoretical way of proving that a function is 1, 1. Thus, we have to prove that whenever f of x1 equal to f of x2, then x1 equal to x2. We have the solution. We have f of x equal to 2x. f of x equal to 2x. Let f of x1 equal to f of x2. Let f of x1 equal to f of x2. That is, f of x is 2x, therefore f of x1 is 2x1. 2x1 equal to f of x2 is 2x2. f of x1 becomes equal to f of x2. 2x1 becomes equal to 2x2. And it implies that x1 equal to x2. x1, if we cancel 2 from both sides, it implies that x1 equal to x2. That is, whenever f of x1 equal to f of x2, we have x1 equal to x2. And theoretically, the function is 1, 1. Now we have to show that the function is onto. To show that the function is onto, the function is defined from set of real numbers R to the set of real numbers R to R. The function f is defined from R to R. Let there is a point y. Let there exist a random point y in the second set. Then we have to prove that the point y should have y has a pre-image in the first set. For any point y in the second set, there should be a corresponding pre-image in the first set. If there exists a corresponding pre-image x in the first set, the function is onto. That is a theoretical way of proving the function is onto. That is, for any y in the second set, there should be a corresponding x in the first set. If x is the point in the first set, its image is 2x. That is, y should be equal to 2x. Let y equal to 2x. Let y equal to 2x. Let y equal to 2x. Then we have x equal to y by 2. X equal to y by 2 belongs to R, belongs to the first set R, belongs to R. Thus, if there is an element y in the second set, that y is 2x. If there is a 2x, if there is y equal to 2x in the second set, there is a pre-image. There is a pre-image x equal to y by 2 in the first set. This is the method we prove that the function is 1, 1 and onto. The next problem is also a similar one. Show that the function f from R to R defined as f of x equal to 3x minus 5 is both 1, 1 and onto. It is a problem similar to the previous one. Let f of x1 equal to, let f of x1 equal to f of x2. Let f of x1 equal to f of x2. Let equal to 3x1 equal to 3x2. If we cancel 3, x1 equal to x2. Thus, f of x1 equal to f of x2 implies x1 equal to x2. Therefore, the function is now to prove that it is onto, let y equal to 3x minus 5. Y equal to 3x minus 5. Therefore, 3x equal to y plus 5 equal to 3x, or x equal to y plus 5 divided by 3. Y plus 5 divided by 3 equal to x, or x equal to y plus 5 divided by 3 is also an element of R, is a real number. Thus, for any x, any y in the second set, any y in the codomain, we have its pre-image. We have an element y plus 5 by 3 in the first set, in the domain. Therefore, the function is onto. Thus, the function is both 1, 1 and onto. Both 1, 1 and onto. Thus, if f defines a function which relates x to y, we can define a reverse function called the inverse of the function from the second set to the first set. For it to happen, the function should be both 1, 1 and onto. Now, the section types of functions is completed. I think you have got a clear idea. If not, please go through the chapter again. And thank you.